And we see how it goes. So steepest descent. So now that we know so much about the gradient and that we are experts on doing 1D optimization, then this is just seems like a natural idea, yes? So if I want to minimize a function, I will step in a point, I will pick a point, and then I will look what is the direction where the function decreases the most, and that's minus gradient, so I will compute that gradient, I will follow minus gradient, and now that's a 1D problem. Yeah, so I want to minimize in that direction, so that's a 1D minimization problem. So I'll just go in that direction until I find the minimum in that direction, and then when I'm in that point, I will look here again, and where is the steepest descent? Oh, now the minus gradient is pointing there, and then I go in that direction. Okay, and I keep repeating it. And in that way, I'm minimizing all the time. Yeah. So this is called steepest descent with the exact line search, because we are actually going to we are minimizing, we move in this direction. There are other strategies where you just, for example, just take the direction and then you say, okay, I'm going to give a step. And then you don't care about minimizing in the 1D. But for now, we're going to look at exact line search. Yeah. So we minimize that n-dimensional function by doing a lot of 1D minimizations. Yeah. So we said, okay, I compute the direction, the steepest descent. That's minus the gradient, and then I will move in that direction here. So that's x case x, the previous one plus on a step in that direction. And then this alpha is taken such that we minimize this function. But notice that here this function is a function of alpha only. Yeah, so it's a 1D function. Okay, you did it in the lab, in the previous lab. Yeah, that's what you did. Okay. So another exercise, prove that if you have a quadratic function, then actually the steepest descent will do this, decay will be this. So this is really saying the gradient is this expression here, yeah? And the alpha, that's more interesting, the one that minimizes the function in that 1D is equal to this value. Okay? Okay, so that's for quadratic functions. So for quadratic functions, we know exactly how the algorithm is going to behave. And we're going to look at it a little bit more carefully at that. Okay, so again here, this is the plot. So we have the gradients and the level sets. And then we are following minus gradients, so we just pick a point. It appears here. And then I will follow minus gradients, so I will follow this direction. Notice that the goal of optimization will be to follow more like a curved path. Yeah, we want to follow the flow. So that direction we want to follow like for infinitesimal time, and then compute the gradient again and change and change and change. Yeah. The problem is if I have to do that, then I have to recompute the gradient in every point, which will take a lot of time. Yeah. So that's why we say, okay, let's follow that direction, and then you can see, well, here that was the minus gradient, but then we come here, and now when I'm here, I'll follow the minus gradient again. So I go there, and then when I'm there, I will follow minus gradient, and then I converge. Okay. So there is a theorem that says, well, if you actually descend, and that's a technicality because, well, most of the time you do, yeah, because we are following minus gradient, so that's a descent direction, plus we are minimizing. How can not that happen? But actually, so that basically happens. But there are some weird functions where that is not going to happen. So if you know that you are all the time descending, and your level set is compact, and we're going to see what that means, then the sequence that you create is going to converge in quotes. That's what it means, this accumulation point here. So I will explain all that. And it will converge to a stationary point, so the gradient will be 0. Yeah. And actually, because it's a minimizing sequence, one can choose something stronger, and is not only the gradient is 0, but it cannot be a maximum. So it can be a saddle point, but actually, what happens in practice, and also if you put some extra function, is going to be a minimum, a local minimum. Yeah. Okay. And notice that this theorem doesn't have much. I'm not putting there many assumptions. Yeah. And I'm just asking the gradient to exist because I want to do a steepest descent. And I'm asking this technicality, that if you put some assumption about, for example, the Hessian about some second order assumption, then that technicality will disappear and the technicality about the accumulation points will disappear. So we will see stronger versions of this theorem later when we do a little bit more of theory. Yeah? But this is really a strong theorem already. It says it converges. Now, there are some technicalities there that I want to talk about. One is the compactness assumption. What does that mean? Yeah? And basically what it means is, well, I have a set. Yeah, my set might be like this. And then I can have two issues with a set that will break compactness. One is maybe the boundary is not there. So it's a set that looks like this. Yeah? And then when I minimize, I will produce a sequence. And then that sequence actually is going to the boundary because the minimum happens there in the boundary. Yeah? But because the boundary is not part of the set, yeah, I don't converge to a point that is in the set. So it's an attainment problem. And then I shouldn't talk about minimization, but I will talk about taking an infimum. Yeah? Okay, so that's a technicality there. If the boundary is not there and I'm minimizing, it might happen that my limit point is in that boundary which is outside the set. Okay? The other problem could be if my set is unbounded. Let's say my set grows like that. Yeah? Then I can just keep moving. My sequence can just keep going in that direction. Yeah? And therefore I will not converge. Again, because the minimum maybe happens there. So an example here will be if you try to minimize 1 over t such that t is bigger than 1, for example. Then when you do that, this is unbounded. Yeah? And your minimum is when t goes to infinity. It's 0. In value, and t is never attained. An example here will be minimize t such that t is bigger than 0. Then here is the infimum, is t is equal to 0. Yeah, but you don't attain it. Then you're in this trouble. Okay? So this compactness assumption, what it's saying is, well, you take your first point, x0, and now you take the level set, f of x. Actually, you take the sub-level set, that is all these things that are here inside, less or equal than f of x0, and then it happens to be compact. Yeah? The two things that you want to avoid are these two, the boundary issue and the unboundedness issue. Yeah? That's why we need that assumption. I'm not saying that the function has some behavior infinity. No, I'm just saying, well, if I take this level set, this sub-level set is compact. Okay? That's what I'm asking. So it's kind of, what I'm trying to say here is that's a very natural assumption for optimization, because we want to avoid these two issues. There is no way to get around. So this is not an issue of steepest descent, this is an issue of optimization. And this might happen with any algorithm. Now it says, well, you run, if you have your level set, and you start at this point, yeah? You start at x0. So you start here, and then you start running, and then you generate points. And then this sequence, notice that I'm generating points here inside this, and it could be really crazy, depending on the function that I'm using. So it could be like this. And it looks like it's not converging. Well, what it says is, if you look at the sequence now, the infinite sequence, what is going to happen is you are going to see that it has accumulation points. And that means points where the sequence spends a lot of time. But it might have more than one. So it's not a limit. A limit is an accumulation point, but when there is only one. But here there might be more than one. It might happen that the sequence starts, I come here, then I go there, I come here. In the even cases here, in the odd cases here. Yeah? Something like that. Imagining the sequence, I don't know, -1 plus 1 over n square to the n. So if I am not mistaken, let me put something, just this one, because this one is going to, with that one over n will convert somewhere else. This one. So in the even case is plus 1, in the odd case is -1. So this sequence doesn't have a limit, but it has two accumulation points, the +1 and the -1. Okay? So we do that. And then what it says is, well, if it has more than one accumulation point, it's not problem. Just take any of them. Take this one or take that one. Those are my two accumulation points. They behave like limits. And then in the two of them, they are local minima, actually. Well, almost as I said, yeah. What I know is it's a stationary point, so the gradient is going to be 0. It's not going to be a maximum. It could be a saddle, or it could be a minimum. Okay? Okay. So it's a very technical theorem, but it says, well, steepest descent basically works always. Unless you have an optimization problem where not algorithm is really going to work, because it has this type of issues, attainment issues. Okay? Now, steepest descent has a problem, and it's this one. And I don't know if you saw it in the lab, because it depends how you do the plot. But if you draw the lines, the steps, they start behaving perpendicular. Yeah, and that's a big problem. And that's a problem just because we are taking. That's a problem because of the way we are building the steps. So we are here right now. We take minus gradient. Let's say this is xk here. Then I will move in this direction, and then I will stop here at xk plus 1. And then when I take the minus gradient of xk plus 1, this one is going to be perpendicular to the previous direction. Yeah, that's a theorem about steepest descent with the sideline stage. Now, why is that? Yeah, there is a reason for that, and the reason is we know that the gradient is perpendicular to the level curve. Yeah? So when I do this level curve here, the gradient is perpendicular. So I have my level curve here. I know that the gradient and therefore minus gradient is perpendicular, so I have that is perpendicular. And then my claim is, and this line here, this direction, in the point where I stop, has to be tangent to the level curve. Yeah. And then if this one is tangent and this one is perpendicular, well, they had to be perpendicular. Okay? And now the question is, why tangent? Why cannot be secant? Why cannot it cross it? Yeah. So let's see how it works. We said exact line search. So we took xk, we took a direction. Doesn't matter if this direction actually is the minus gradient, it's just a direction. And then we optimize in that direction. Yeah. And now the question is, what is the minimum over this line when we follow that direction? Let's assume that it's not tangent. So it will be like this. Can this point be the minimum? If this is a level curve, this is f of x equal to c. Can this point be a minimum? A local mean? What is the meaning of these level curves? Yeah, if I do f of x c plus epsilon, I will move up. And if I do, let's say 1 here, and if I do c minus 1, I will move down. Yeah, so I will move inside. So, can this point be a minimum? No, because I'm moving inside this region. Yeah, this region here is the region where f of x is less or equal than c. But only in the boundary c, because that's the level curve. Yeah, inside the region, so if I put the region without boundary, inside the region is c. So if in this point my line is moving inside the region, that means that this is not a minimum. My function is still going down when I'm moving in this line. Okay? Again, I'm moving in the line. I get to this point and I ask, are you the minimum? Well, look at my level curve. If my level curve is like this and the line can go in, that means the values here are lower than here. So this cannot be the minimum. Yeah? Now I keep moving, and when I get here, what happens? The value here is equal to the value here, because this is the level curve. Yeah? F of x is equal to c here. And then I know that the values inside are smaller. Okay? So that means that the minimum is somewhere in here. Okay? So let's look at that minimum. So let's say the minimum is this one. What is going to happen at that minimum? Again, we can repeat the analysis. Yeah? So if the level curve is not tangent, that means if it does like that, then again, this is not the minimum. Yeah? Because the points inside have smaller value. So the only thing that could happen is that when I get here, that is tangent. So it touches the level curve, but it doesn't go inside. Okay? Knocks at the door and says, oh, thank you, sorry, I got the wrong door, and then it goes away. It doesn't get inside. Because inside the values are smaller. And that's the minimum. So here at the minimum, the level curve is tangent to this direction, or to this line, and therefore when I do the gradient, that is the gradient is going to point in that direction, and the minus gradient that is going to point in this direction, yeah, then the minus gradient is going to be perpendicular. What is that for that? I don't care who is this direction. That's true for any direction. If I follow a direction and I do minimization in that direction, to find the next point, I will always have that the gradient is perpendicular, minus gradient is perpendicular, or the gradient is perpendicular. Okay? So, you get a plot like this. So if you go and look at the code that you did the previous time and you do the plot, you will see that. Okay, and do it because it's nice when you go and see that actually the theory is something that happens in practice. Okay, and why is that a problem? Because I said that's a problem. I didn't say theorem or characterization or whatever. I said problem. Yeah, why is it so bad that it goes in this zigzag behavior? Why could that be bad? Yeah, well, some people will say, well, because this really means you want to move in that direction, but you stop. Here you want to go down and you want to go to the right. But you go down a bit and then you stop. And then you go to the right and then you stop. And then you go down a bit and then and then you are stopping, and then zigzagging is not a good idea. It would be better if you just go down all to what you need and then you go to the right all that you need. Yeah. But that's maybe too much to us. To be able to guess the whole length going down and then the whole length going right and doing just in 2 steps, that's too much. Yeah, but that might be too much. So it might be okay to go down sometimes and a little bit up and a little bit. So I don't think that's a good explanation of why zigzagging is a problem. Okay. So if you do the plots, here is not really a problem. Yeah, here you go and then you go down and to the left and then down and you are there. But here you can see that's a problem. Yeah, and the problem here is, because you can see this function is kind of a valley here. So it's very thin here. And then you go perpendicular, but you go perpendicular in the wrong direction. If you started somewhere here, you actually will go in this direction and end up here very quickly. Because the gradient here points there. Yeah? But if you start here, your gradient points there, in that direction, that is perpendicular to the valley. But it's not. But again, if it was perpendicular, then it would be okay, because then in the next step you go there. But here, you are neither perpendicular, neither parallel. You are like 45 degrees. Then when you go perpendicular to the previous direction, you go again 45 degrees in that valley. Yeah? And then that's a problem. Okay? So you did it in the wrong direction, and then you start zigzagging. You cannot go much more because the valley starts going up here. So you have to now change. You go there, and then in the next one you go there again, and then that's the problem. So it has to do with that function there is a nicer rounded with one. Here, this is more elongated. Yeah, when I look at the curvature, so it has to do with the curvature. Yeah, here is more like rounded ball. The level sets are closer to a ball, but here they are more elongated. They are elongated ellipses. Yeah, and what we're going to see is that actually it has to really do with the length. When I look at this ellipsoid, the maximum length versus the minimum length. And these are related to the eigenvalues of the matrix that I'm using to do these plots. Okay, but we're going to get there. But that's what characterizes how fast is this algorithm going to converge. Okay, so if you remember the Rosenbrook function, yeah, so I said that we're going to use this function to test different algorithms. And if you run a steepest descent, starting in that point, let's say, there is something wrong with my plot there because I don't know why my first step is like that. It's not right. So let's say you start in the second one, and then you go, and then you start moving in this zigzagging, yeah. And then if you look here, the zigzagging, you can see it there, yeah. And then the nice feature about this function is because the valley is not a linear valley, but it's a curved one. What happens is no matter where you start, you end up in this zigzagging in the valley, suffering from the fact that you want to put this zigzag there. Okay? It doesn't matter if you start here. Well, you go there, and then you start again zigzagging, and in some point, because of the curvature of the valley, your zigzag is not in the right direction. Or let's say, because of the curvature, in some point, your zigzag is in the wrong direction. And then you start giving smaller and smaller steps, and then in some point, the numerics kick in. Your computer says, I think we already converged because we are not moving anymore. And then you stop, and then you are really far from the optimum. Yeah? Or even if you had GUTS computer with infinite precision, yeah? Well, no, in GUTS computer that won't be a problem because there you have infinite time. But if you have a computer working with infinite precision, then because the steps are every time smaller and smaller, you won't be progressing so much. And then you will get stuck. Yeah? So it's not just a precision issue, it's really the issue that because you are perpendicular, you are moving in the wrong direction all the time. So you cannot move much. Okay. Okay, so what can you do? Well, we can say, well, following the gradient, maybe the problem is because we want to do minus gradient. So we are being greedy. Yeah? Locally, when I am sitting in this point, the best direction seems to be the minus gradient. But then globally, that will give me this zigzagging. So globally is not a good idea. So we can avoid that. And then the idea is, well, take any direction, yeah, and then compute a step. Again, remember, the problem with the gradient was not the previous direction, but the direction that I'm taking now. So I can take just any direction, yeah, that is different from the gradient, let's say, but I want something that is a descent direction. So before we were taking the steepest descent, now I want something that is a descent direction. And what does it mean to be a descent direction? How can I see that if I follow some direction, then I will go down? Because then we're going to do a subline search. We're going to say, okay, find the alpha such that this is... Actually, here I'm not even doing a subline search. I'm just saying, just pick any alpha where you get some decrease. Yeah? And then you update, and then you go back to 1. So just follow the best direction. Yeah, the steepest descent. Just follow some good direction where you're going to descend. And then actually don't compute the best alpha. Just compute some good alpha, and then repeat. And that will avoid some issues. Because, yeah, actually, if I have picked this point here where it was not the minimum, then it won't be tangent to the curve, and then I can actually pick the gradient in the next step, and I'm not perpendicular. Yeah. Remember, the problem comes here from I'm doing a subline search, and then I'm doing the minus gradient. So these two are perpendicular. If I don't do a subline search, then this is not perpendicular anymore. I can't even pick the minus gradient there. Yeah. So I can solve the issue in any of the two or in both. Just compute any direction and then step length. But I need a direction that is going down. How do I know that a direction is going down? How can I do that? So let me tell you some of the most modern ideas. One of the most modern ideas is just pick a random direction. If you don't go down in that direction, then you go down in that one. Yeah, because your derivative, if it is positive in that one, is negative in this one. Yeah, and actually you can compute the probability that the direction is good, meaning I can use this plot again. If I am in this point, in which directions do I decrease the most? Well, here in the minus gradient, yeah? Maybe I'll do another one with not so much information in it. This one. So if I pick this point, we said the steepest descent is this one. Yeah? But anyway, all these directions are good. You are descending quite rapidly there. Yeah? So if I pick a random direction and I pick either these ones, because I will pick a random one, and if I see that the derivative is positive, then I will go in the other direction. So if I pick here or here, I'm good. Yeah? And here, this direction are not growing so much like this one, there is no growth. Yeah? When I pick this direction, I'm just going over the level set. So my derivative will be 0. Because this direction is perpendicular to the gradient. Yeah? Remember, directional derivative is equal to gradient transpose D. Yeah? So I want this to be a negative number. So what I need D, if I look at the gradient, what I really need about D is that D points. So this is the perpendicular line here. I need that D points in that direction. Any D pointing there, yeah, will be a good direction. So to be a descent direction, that will mean that this quantity needs to be negative. Yeah? And that means half of them are descent. Yeah? So all the directions that go below this line, they are descent directions. Because the inner product with the gradient is with the gradient is negative. Yeah? Here the inner product, let me point this one here because this is very important. This direction D here, let me call it D hat, has the characteristic that the gradient of F transpose D hat, the inner product, 0. So there my function doesn't grow, the derivative is 0. Yeah? And for all these directions, my function is growing. So what I really want to do is to go inside this region, this sublevel set. Yeah? And then for that I just need, well, these directions are not that good. It's better to have this one closer to the minus gradient. So if you pick a random direction, actually somebody computed the probability that you get a good direction, and that's something like 1/4 even for high dimensional space. Yeah. So you know that if you pick a random direction, every 4 steps at least you're going to be doing a good move. I mean, you expect to have a good move. So random direction search, that's called the method, actually works pretty well. So you can show that you have progress every 4 moves, and then you can actually quantify that progress, and it works pretty well. Yeah. So that's one of the modern methods. Don't put so much effort into getting a good direction. Just pick a random one, and then you're going to be lucky. But again, it's because the probability of getting a good one is something like 1/4. If it was tiny, then you had to be really lucky to hit a good direction. Yeah. Another method is called coordinate descent. So just go through the coordinates. Look in the direction of x1, and then in the direction of x2. And then if x1 doesn't work, then use minus x1. If x2 doesn't work, use minus x2. And so far. And then you go around all the coordinates. And that method also works pretty well. Yeah. So now the question is, why are we going to spend so much time and effort explaining some good directions? Well, because these methods actually we can prove more. And actually they give us some idea why the other methods work well. But as I said, this is more machinery. Like random descent was proven to work no more than a decade ago in a very good general fashion. It was known to work like for quadratic functions and for some other special cases, but now it's known to work. So it's mathematics being developed no more than a decade ago. Okay. So again, what we're doing is we are reducing optimization in n dimensions to many optimizations in 1D. And then the question is how to pick a direction, and we just say, well, you can even do random directions, you can even do coordinate descent, but we want to discuss a little bit about that. And then the other question is, when do we stop? We haven't talked about that. Yeah, so we have to clarify those. So one of the first ideas was, well, on how to pick directions, was this conjugate gradient methods. And then the idea is, well, this gradient is giving me trouble because of this perpendicularity, so let's use a method that somehow avoids that. And then the idea is, well, if I do this direction, yeah, so let's just do the animation. So we come here, and then what is the minimum there? So if I do a sat line search, where I'm going to stop. Okay, so we go, yeah, here we are decreasing. When we are here, we will start increasing. So we're going to stop here. Okay, so we stop there, and then if I follow the gradient there, the minus gradient, it will go down. Yeah, but somehow, I have to keep some kind of memory that actually I was going in that direction to the left. So what I will do is, instead of using the minus gradient and forgetting my previous direction, what I will do is some combination between this new direction, the minus gradient that is being proposed to me, and the old direction. Yeah. So for the particular case that I bring here, this is called conjugate gradient, but some people call this about momentum, and it's like you are moving in that direction, and then when you stop, you don't do a hard stop and then start moving in the other one. It's you are moving in that direction, and then you have momentum. So when you try to move there, you just keep moving in a combination of the two. Okay. So this is called momentum methods. And they are also very, very, because they many momentum methods were better than, for example, random direction or coordinate descent. Okay, so you get a direction that goes as a combination of the two. Okay, and then, well, then your new direction will be a combination of minus gradient plus the old direction. And then the question is now, how do you pick that beta? Yeah. And there is where hundreds of betas have been proposed, because this is an idea that has been around since the 70s. So there has been hundreds of papers, literature, about how to pick this beta, and I can show you some of them. So this is the Fletcher rivers and the Polar River, let's say like the ones that are known to work best in theory and practice. So some directions have been proposed because in theory they work well, but then when you go into practice, they don't work well. Yeah. And actually, nowadays there is also a direction or a method that works well in practice, but we don't have a theory to explain that yet. So with all these machine learning models, they use some ideas and they work, but we don't understand yet why. But this is ones that they work well in practice and in theory, yeah. And the point is, these ideas, they come from really looking at second degree functions, so quadratic functions. Yeah, so you look at a quadratic function and then you said, okay, what works well for a quadratic function? And again, the idea is when I'm close to my minima, my function will be close to a quadratic function somehow. Yeah, because of this Taylor approximation will work. This second order Taylor approximation will start looking like my function or something like that. So the idea is that's why these methods work. But as I said, there has been a lot of directions proposed, and they are all based on the idea of, oh, this works well for quadratic functions, but they don't work well in practice. Yeah. But these ones work well. Okay, so this is about this conjugate direction, and then I will explain more. I mean, it becomes very technical. Okay, but the idea is we want to combine, we want to avoid, and then again, I have a lot of possibilities here, and those seems to be good. Okay. So why do they work well for quadratic functions? Because they get some information about the Hessian, yeah. So and then there is a link there. Okay. So what happens when we do conjugate gradient? So you see that because we are doing conjugate gradient, we are learning a little bit about the Hessian. We are learning about the curvature of the function. So here in the Rosenbrook, the steps they start going around. It takes 98 steps to converge, but it does converge. Yeah? And remember, the function value is 0 at the minimum, and here we get 2 decimals. Okay? So it behaves better than steepest descent, which didn't converge. This one does converge. Okay. And this was with the subline search, because there is explicit line minimization, means I'm doing a subline search. Okay. So now we're going to move on, and we're going to use S again. We're going to still pick a direction, but then what we're going to do is we're going to do Newton's method. So to pick that direction, we're going to use the Hessian. Yeah? So that means somehow we're going to use the information about the curvature of the function. Newton's method, as in the previous case, is based on Taylor's approximation. So let's do this before we stop the lecture today. So suppose you want to minimize this function. Yeah? So you want to find the best delta. You are at x, and you want to find the best delta. Yeah? This is exactly what we did in the 1D case. Now we're going to do it in multi-D case. And then the Taylor approximation, remember, f of x plus delta. We did it for will be an approximation. So this is f of x plus, and then I will take the gradient. There I wrote g for the gradient. So the gradient transpose delta plus, now I want the quadratic one, so I had to add a quadratic term, and this is going delta times the Hessian of my function. Okay, so that's the approximation that I'm going to use. So I have my multi-D function, and I'm going to do a quadratic approximation, and then to find the next point, here x is fixed, so what I'm going to do is to find the delta that minimizes this quadratic. Yeah? So one point that is important here is, because I want to minimize this quadratic, minimizing, let me call this quadratic p of x. So the big question there is, what do I need for a quadratic to have a minimum? Do they always have minimums or not? Yeah?
It should be convex.
It should be convex, meaning, in terms of the algebras, yeah, it should be like this. Yeah. So what happens in 1D? Let's look at a 1D. What quadratics do we have? Basically, we have 3 types of quadratics. Yeah. So we have, the quadratic in 1D is at squared plus bt plus c. Algebraically, there is only one type, but when we do it geometrically, it could happen that a is positive, yeah, and therefore we are like that. Yeah. Or it could be like this. Yeah? Whether it's this case or that case depends on what? As I said, depends on A. Yeah? So if I'm here, A is positive, and if I am here, A is negative. Does that ring the bell for everybody? Okay. What other type of quadratics do we have in 1D? There is a case missing here. Yeah. What happens when A is 0? Yeah? Yeah. When A is 0, we have a line. That's still a quadratic. Okay? So if that is a weird quadratic, we usually don't call it a quadratic, but it's still a quadratic. Okay. So, to have a minimum, we need to be in this case. Yeah? Otherwise, here the minimum goes to minus infinity, and here the minimum goes to minus infinity. Okay? Or the minimum value is minus. Okay? So we need to be here. So we need A to be 0. How does that translate to the multidimensional case? The multidimensional case is even crazier. So what will happen with... So now in the multidimensional case, our quadratics, how do they look? Well, usually it's X transpose AX plus B transpose X plus C. Here A is a matrix, and it is convenient, and in this course we will always do it. We're going to assume that it's symmetric. Yeah, doesn't have to be symmetric for a quadratic. Even if the matrix is not symmetric, I have a quadratic, but it's convenient to have a symmetric. And we can always assume it, yeah? So any quadratic, I can write it as a symmetric one, because this quadratic is equal to this one. So if it is not symmetric, I can symmetrize it. Okay? So this is a, check it out. It's an exercise. Okay, so I can always assume that it's symmetric. B is going to be a vector, and C is just a number. Okay, and these are all my quadratics. Now, how do they look like? Do we have the same three cases? Probably you have seen it. You can have this type of quadratics. Yeah? I mean, in our curve level set plot, it will be something more like this. Yeah? And you can have this type of quadratics, which actually have the same level, but going in different order, reverse order. Yeah? So the level sets of these quadratics, they are ellipses. Yeah, so I put it there here more like circles, but they can be also like this. Yeah. Okay. What else do we have? And this is called positive definite. This is called negative definite. So this is the case when A is positive definite, actually. And this is the case where A is negative definite. I wrote the same. There is a very famous or infamous quadratic. And in 2D they already happened. Plane? No, the plane is very famous. So, and that one is the same as there, yeah? So if A is equal to 0, we have a hyperplane, okay? But another one. So if the matrix is positive definite, we have this. If the matrix is negative definite, we have this. If the matrix is 0, we have this. Now, do all matrices have to be either positive definite, negative definite, or 0? Yeah? I mean, we're going to recap this in some lectures, but positive definite means all eigenvalues are positive, or not negative, let's say, greater or equal than 0. Negative definite means all eigenvalues are non-positive, so less or equal than 0. Yeah? So, do all matrices have all the values non-negative or non-positive? No, yeah? We have matrices that have positive and negative eigenvalues. So, how will that quadratic look like? So, let's think in a very quickly, a matrix with a positive and a negative eigenvalue, this one, and then the corresponding quadratic is x squared minus y squared. Okay? And then because we are just off time, then as a homework, plot this quadratic. Okay? Go to a computer, a Wolfram Alpha, and plot it. Because that's what I was going to do, but I run out of time. Now you have to do it. Okay? And then see you next time. So send me the link and I will post it in Canvas. Send me the link and I will post it.
Sure.